for coming to my talk, ladies and gentlemen. And my name is Zilong. And before before my presentation, I would like to have some very brief introduction about my university. And so the University of Essex was actually is actually a very young university, founded in 1965. And in UK, we have many universities, and some are focused on research, some are focused on the and the University of Essex is very unique. And so in and let's see, no, I cannot write, it's hard. You see, and University of Essex is very unique, and because it actually excels both in the research and the higher education. In 2000, so for example, in 2018, we actually got the award of University of the Year, and in UK, you know, we have a very prestigious ranking, which is called a ref ranking. It is a national ranking for all the UK university, and the University of Essex is actually one of the top 20 in our last ref competition. And in terms of location, here is London, and this is Cambridge, and the University of Essex basically is just a train to London, and 1 hour by 1 hour to Cambridge by car. And the main campus located in Colchester. It is it's a very old town. So my school is called CSEE, Computer Electronics Engineering, and it has the strengths in AI, machine learning, neural engineering, and robotics. And my research is actually focused on communication. And of course, nowadays I'm also using some machine learning AI to do the research on the communication. And I have used a number of tools from the coding, signal processing to address some communication problem. And so here is just a very brief timeline about my research. If you want to know more details about my research, you can just go to this my Google link. And I joined the University of Essex in December 2019. And before this, I worked as a senior research fellow in University of Surrey. And so this the talk that I'm going to present is actually mainly based on my research from University of Surrey. And before this, I spent many years in Singapore after I have got my bachelor degree and master degree from China. And so the title of this topic is on the new laws on codomain NOMA. And so NOMA is a very new and emerging techniques, you know, for the 5G communication. And nowadays we have two types of NOMA. One is the codomain NOMA, the other is the power domain NOMA. Basically, the power domain NOMA is you know, for that one, it's actually for different user, they will use a different. So for that one, you know, different user will actually use will use different you know, power level. Whereas for the codomain NOMA, different users are separated by code books. So I will first spend a few slides to introduce the research background, and then since this talk is on the on the codomain NOMA. So we have two types of codomain NOMA system. One is based on the sparse codable, the other is based on the dense codable. And so I will show you a lot of comparison results. And then in the last part, I will give out my and the future work. And this talk is actually based on my new my paper right here. If you have any mobile phone, you can take a picture for the link here. You can actually get this. You can actually get the full paper from this link here. Yeah. Now mobile. So this table shows us the mobile evolution from 1G to 5G. And 1G actually started about 40 years ago in 1981 with a very small data rate, 2K. And so actually at that time, the 1G system can only provide very basic voice communication. And of course, the mobile phone at that time was, were very bunky. But starting from 1G, we have 2G, 3G, 4G, 5G. And in UK, we already have 5G network in use. We have many cities, and we actually plan to from 4G to 5G, and the same can be said for some other country. For example, Korea, Singapore, and China. I believe this will also be the same for India. And so basically this table, and you can see that we have in terms of the data rate, that is becoming higher and higher. Starting from 2K and then 5G actually aims to support the data rate of up to 10 gigabit per second, or even higher. So now the question is, what's the major difference between 4G and 5G? And can we simply say that for 5G means a higher transmission rate? So I'm going to answer this question today. So basically, we can see that in the 5G era, we need to support more and more user and more application. So basically, and essentially, 5G needs to support more and more vertical industry. For example, smart home, smart city, smart health, and right now you can see from this picture that we're able to target the use of 5G networks for the remote surgery, and we can also use the 5G for the to provide the autonomous driving. And in addition to that, another very promising vertical industry is for the factories of the future. So compare with 4G, and we can see that a major motivation for us is that we need to provide the machine type communication for mass connectivity because of a wide range of vertical industry. And from this picture, you can see three pictures for a factory in Taiwan. And just now I have mentioned about 5G can be used for the factories of the future. Now the question is that what does this mean for factories of the future? And for that, I would like to introduce a little bit about the Clear 5G project. You can load down this the link here, and this is the page of this Clear 5G, and and there are many Clear 5G deliverable report which are open for downloading. And basically, this is the EU and Taiwan project. In EU, you can see partner here. Taiwan, we have many partner here, and the Clear 5G is a very good is the project really focusing on the machine type and URLC. URLC refers to the ultra reliable and low latency communication. So basically, for the 4G system, and the latency is in the order of 100 millisecond, whereas in the 5G era, for some mission critical communication, we aim to provide the latency down to 1 millisecond and with the reliability of 99.999. So this percent. So this means that if we need to send out 1 million packet maximally, there we can have only one packet in error. So and of course for machine type communication, we require that many communication sensor devices should be highly the energy efficient. So so this also requires us that how we need to improve our the transmitter signal design as well as the signal processing algorithm at the receiver. Since we need to support the activity for machine type communication, so naturally we need to design a multi-user system, and for that we need to use some advanced access technology. So with if you look at the traditional the traditional multiple access technology, and in the 1G in 2G system we use TD, 3G we use CDMA, 4G we use OFDMA. Now in the 5G we use NOMA, non-orthogonal multiple access. So regarding to this NOMA, and if we consider the codomain NOMA, so the question here is that it is very similar to the traditional CDMA system. So we can say that the codomain NOMA is actually largely inspired by the CDMA system. And of course, from this point of view, we can say that essentially CDMA is also a type of NOMA. But actually, the major difference here is that the codomain NOMA system design for the 5G communication system, that is mainly for the support of massive connectivity. So in the 5G, major important the codomain NOMA system we call this SMA. The most original idea on SMA, let me remove this one. Yeah, so one of the most important the emerging codomain NOMA is called the SMA. The most original idea is called the LDS, and this was actually published in this paper in 2008 by researchers from University of Surrey. And this is the transmitter. This is the receiver. At the transmitter side, we can see multiple users. They do modulation and they do the sequence spreading. At the receiver side, we can see the equation y equals to hx plus w. And so essentially at the receiver side, we need to solve this equation. All right. This equation, actually this is rank efficient equation. So this means that the channel, which is H, is actually a fat matrix. So this is the channel matrix. Fat matrix means that the number of variables that we need to solve is actually larger, is much larger than the number of equations that we can have. So which is can explain to have this fat matrix. So this means that if we need to use the maximum likelihood receiver to do the decoding, so we will suffer from a very high complexity, which is in the order of m to the power j, where m refers to the modulation order, where j refers to the number of user. So how we are going to solve this equation? So the major difference from the traditional CDMA is that in this LDS signal, we use the no density signature. So that refers to here you can see an example here, and basically we will have very sparse sequences because of the sparsity, and so we are able to relate this system equation in a factor graph right here. So for example, we have 12 time slot, and we have 16 user. So in this case there, we can write out, we can and relate it to this factor graph, and then we can use the massive parsing to decode out this to solve this equation in a very efficient way using the massive parsing. So this idea was adopted later on by Huawei, and so in 2014 got this US patent. If you look at here, so basically we consider for the frequency domain, we have 4 subcarrier, but we have 6 user. Okay, and you can see that if we use the OMA transmission, all right, if we use the OMA transmission, then maximally we can support 4 user, whereas here we can support 6 user. So because of this, so we are able to provide the overloading factor of 150. And so here you can see an example from this thing here. And so you can check this code book. And so basically for the when we do the encoding, this is for the user 1. If user 1 wants to send a 111, then we will just select out this code word. So this will be the code word for the user 2, user 3, so on and so forth. So all the user, they select their own the code word based on the input message signal, and then these code words, they are superimposed together, and we form this vector. Normally I call this a superimposed code word. And the strength of SAMA is that it actually combines the strings of coding and modulation together. So because of this, it actually enjoys the so-called constellation shaping game. The question here is how we design such sparse codebook. And suppose that the vector X is my transmit superimposed code word. At the receiver side, because of the noise and because of the multi-user interference, so the receiver may decode out the transmitter vector as y. Okay, so basically, x does not equal to y, and we can always calculate out this PEP. All right, so we call this pairwise error probability, and we can see that this PEP is actually upper bounded by this value. Okay, it's upper bounded by this value. So now the question here is that we if we want to minimize this guy, So we just simply need to minimize the upper bound value. So, so this actually refers to the product of multiple fractions right here. And it turns out that we just simply need to maximize the minimal product distance. Okay, and for that, how we can achieve this? So basically, in the communication theory, we have two important types of concept, which is called the coding game. The other is diverse order. So in order for us to design very good code book, we wish to design certain multi-dimensional constellation such that you can enjoy a higher diverse order and as well as a higher coding game. Okay, we will come back to these two concepts later. And so far, the optimal SMA design is still open, and most of the current design start from multi-dimensional constellation, and starting from this mother constellation, and then we apply a series of the different operation such as the constellation rotation, interleaving, and so on and so forth. So this actually gives us the example here. And basically, so far the design the current design is actually channel sensitive. So that means that some design is only for the downlink channel design are for the uplink channel. This short paper published in 2019, we have designed some new sequences, and for that we call this the proposed LDS. And if you look at that green curve, we have compared our BR performance with that of the Huawei codebook, and you can see that our proposed codebook is able to achieve the comparable BR performance in the relay feeding channel. But whereas once we come to the AWG channel, and so the performance gain is you can see a performance gain here. In terms of the design of codomain NOMA, we have numerous proposals from submitted to GPP, and you can see this two paper here, and they have provided a very good survey work to this research. And so this is for SCMA proposed by Huawei, and also we have a PDMA proposed by CAT. And in addition to that, we also have a number of schemes based on sequence spreading. Now, among so many different codomain NOMA scheme, you may wonder what's the problem, what's the weakness of SMA system. The major problem of one of the major problem is that from very limited diversity order. Just now I have mentioned about this the concept of the diverse order, and ideally we wish to increase the diversity order, as much as possible. But the concept of the principle of SMA is actually similar to the CDMA system, where each user, so basically we have 6 users, 4 subcarrier, and so each user will spread its signal over 2 subcarrier. So because of this, so this system can only have the maximum diversity order of 2 for the uncoded system. All right. So now the question here is that how we are going to improve this SMA. Okay. If we want to increase this diversity order. So that means that the resultant system can enjoy better BR performance. But in this case, we won't have such a sparsity anymore, and we will the resultant multiple access system will be dense. So this is a major motivation. We started the DCMA. So how we can design such a system? We know that in a multi-user communication system, we have for the message B, and we can always send out a signal using generator matrix, and this generator matrix corresponds to the spreading sequences or the generator or some precoding matrix. So the question here is how we can design a very good generator matrix G such that you can enjoy a very large minimal product distance. In order for us to do this, let me introduce you the square matrix V. And so this one refers to the transpose of a random matrix, and it is a function of a multiple variable theta 1 to theta n. So this matrix is a square matrix with order m times m. We have a number of construction reported in this two paper, and so for each construction we are able to generate a square matrix, and so those matrix can be used as a precoding matrix or a transform matrix. Each of them they have a very large minimum product distance. So we can generate such a dense codebook using the COM modulation. We just simply generate a square matrix n times n, and then we just randomly select a few rows from this square matrix. So with this we can, so basically if we let n to be 6, q to be 4, and we are able to provide the same overloading factor as that of SMA. Here I'm giving you an example. Suppose that the m is 6, and using 3 we can generate this different variable theta 1 all the way to theta 6. So with this, then we can simply just generate this 6 times 6 square matrix M3. Then we just select 4 rows, right from this square matrix. Then with this, and then we can support the overloading factor of 150. All right. So how we're going to decode out this DCMA? Here we propose to use the generalized sphere decoder. Sphere decoder is actually a very famous detector for the MIMO detection. But the traditional decoder assumes the fact that the system and equation should be full rank, whereas here for the codomain NOMA system, our system equation is actually rank. So in order for us to decode it out, so we actually use this sphere decoder, and we actually follow this paper right here. All right. So we in the next few slides, I will present you a lot of simulation result to compare SMA and DCMA. So in this slide, I'm showing you I'm comparing with the complexity of two type of setting. One is 4 times 6, the other is 5 times 10. For the 4x6 NOMA setting, we can see that the DCMA actually enjoys a lower complexity. But once we move to the 5x10, in this case, if we look at this blue curve, so that means that SMA enjoys lower complexity. But actually, for these two, in terms of the complexity, they are comparable. So how about the PPR for the downlink channel? Because to use for us to transmit both DCMA and SMA system, so we can we need to consider the PPR issue at the base station transmitter. And here we have considered three types of number of subcarrier setting, to be 64, 1024, and 8192. With this for all the setting, and we can see that DCMA enjoys a lower PPR. Also compare that the encoded BR between these two systems. And in the left-hand side, that is channel, the right-hand side, that is for the uplink channel. Now, if you BR performance of DCMA, so compare with the BR of SMA, and we can see very clearly that the BR of DCMA enjoy a steeper slope. So if we relate this to the diverse order, and we can see that actually this, we can see that DCMA indeed enjoys a higher diverse order. For this system, the diverse order equals to 5. Whereas for this case, SMA, it can only enjoy the diversity order of 2. Also compare the BCH coded block error rate. And for this case, we consider a lower rate, which is about half, where for this case, we simulate a higher rate. And we can see that for each case, if we consider DCMA with SMA, we can see that DCMA enjoy a better block error rate. So basically, for this two systems at the block error rate of 10 to the power -3, we can enjoy about 1.5 dB again. We have also compared the SCMA and the DCMA using the turbo receiver, which is shown here. So basically, we first do the OFDM demodulation and the code domain NOMA module detection, and then we're using turbo to do the decoding. And here shows the comparison of a block error rate. And now, if you look at the block error rate of this red curve, so that refers to the LDPC coded SMA system. Whereas for this the dark red curve refers to that of the DCMA curve, and you can see that DCMA still enjoy better block error rate performance, and the same can be said for the other code rate. And we have so this is for the 4x6, and this refers to the 5x10. And for the different setting, in all the cases, we have shown that the block error rate of DCMA is better. And as you can see, that we have also compared our the block error rate with that of for the DCMA with the linear receiver. All right, and you can see that when the overloading factor is low, and the coding rate is also low, and basically using the linear receiver can work. However, once we increase the code rate, And once we increase the overloading factor, and you can see that the a linear receiver for DCMA does not work anymore. I have finished my talk, and so in this talk, I have introduced the SMA and the DCMA. And I have shown you that the DCMA can be designed to enjoy the full diversity order. So that refers to significantly improve the BR performance. And for this, we have used the generalized sphere decoder, and we have compared the complexity as well as the PPR. And in terms of the complexity, both systems enjoy a comparable complexity. In terms of PPR, generally speaking, DCMA is lower. We have many future works for this. For example, for the large scale DCMA system, how we can further reduce the complexity. For that, we can suggest to use the EP decoder, and so of course the convergence analysis for the different codomain NOMA system is also a very interesting topic. And nowadays there are several works on the using the deep learning for code book design and detection. So the main result of this paper have been reported in this paper. Okay, thank you.
Thank you so much, sir, for taking out time and explaining everything so beautifully. If there
Thank
are
you.
any questions that you'd like to ask, sir, please write it in the chat box. This is a request to all the attendees that if they have any questions, please write it in the chat box. All right. So I guess there are no questions in the chat box, so we'll move ahead. And with this, I'd like to thank sir for being here, for being so patient and explaining everything in such a detailed manner. I'd like to thank you on behalf of IEEE MSIT. I'd also like to thank Professor Anubha Gupta of IIIT Delhi for making this happen. And lastly, I'd like to thank all the attendees and SPS Delhi
Sorry to
for
interrupt.
making this.
Uh,
Sure.
yeah, I think there is a question coming.
Sure.
Okay, we can wait for a while.
All right, we'll wait for a while. If there are questions, we'll take those up.
So, till that time, sir, can you just help us to know what are the major challenges that we may face in the 5G network that we might have to go ahead with the new technology of 6G?
Sorry, can you repeat your question again?
Can you help us to understand what are the major challenges that we might face in the 5G technology that we might have to go ahead with the 6G technology?
Yeah, I think that is a very good question. Yeah, so yeah, and you can see that in many countries and many university, people now are doing the research for the 6G already. But I think 6G will be quite different from 5G, because 6G, that will means more AI, more machine learning. So that will be that means that our communication system that will be more intelligent. So essentially from the design point of view, and I think now how we are generally leverage the tool of AI, particularly for the such kind of codebook design or for power domain NOMA, and so in terms of the physical layer technology. And now we are we are doing this research now. Yeah, so I think the major issue here is how we can leverage the AI. Thank you.
Okay, so I had a question. I put it on the chat window as well. So you have suggested at the end that we should be using expectations propagation decoder, right? So
Yeah.
do we have so far any research on that you earlier you used a GSD decoder? So was it any better than the GSD one? Is there a research?
Uh, yes, yes. There are already some published paper on the EE-based decoder for MIMO system already, and the major motivation for that is that EP detector um, results in much lower complexity. So yeah, but whereas in terms of the performance, one that it will be close to that of the generous sphere decoder. So if you are interested in that research, you can probably you can send an email to me. I can forward you some paper, and if you are doing this research already, probably we can work together. Yeah.
That would be great.
Yeah.
Okay. So
Good.
anyone
Good.
else has any? Okay, please. So anyone else has any questions can put them in the chat. I think we had one. Somebody was asking. I think Paras Jan had given.
Yes, yes. Actually, I asked for the mic access because it was a lot to type. So, Dr. Liu, thank you for the enthralling session.
My pleasure.
My question was that there has been recent work done by Lin et al. For the deep learning approach, as you mentioned in your talk, in your concluding section, that deep learning can be used for uh, DCMA techniques as well. So they have used it for XCMA. They have
Yeah.
used deep neural networks for sparse code multiple access,
Yep.
and they have even shown that there's uh, a better result in terms of BER. So
Yep.
what are the problems and what are the obstacles when applied to DCMA that are currently being faced?
Yeah, I think right now you can see you have mentioned that there are already some paper using deep learning, for example, the autoencoder to design some new codebook. And if you look into those paper, actually they just focus on the Gaussian channel. So, but once we move to the relay fitting channel, I think those deep learning and tool may not work very well. So the question here is still how we are going to fully use the power of AI machine learning such that we can design our system for more complex channel. Because once we have the relay fitting channel, each time when we run our simulation, we will have the new channel fitting game. So in this case, that we can see that the code book generated from AI or from the deep learning tool may not work very well. Yeah.
As far as I understand, pardon my paucity if I missed out something, but if we can incorporate the relay fading channel and for DCMA, then the results might improve, right?
I mean, right now, even for the sparse codebook design and for DCMA system design, the current research, basically they all focus on the Gaussian channel. So it is very, basically the design using deep learning is not effective once the channel is relay fitting channel, because the reason here is that relay fitting channel, the situation is more complex because each time we will have a new channel fitting game. So that means that you need to search the code book, and such the code book will work very well, and then no matter how the channel, the channel fitting game is small or large, and then in total, yeah, that will give me a very good error rate performance.
Very much, sir.
Yeah, yeah, welcome.
Yeah, we have the Q&A also. So, Mohammed Hamza says that thanks, Dr. Zilong. I would like to know speakers' comment to power domain NOMA uh, in the multiple antenna transmission. I repeat, I'd like to ask speakers' comment on power domain in NOMA in multiple antenna transmissions.
Yeah. Yeah, I think this yeah, basically the power domain NOMA, power domain and NOMA is not my major research area, but I believe that there are many paper they consider the integration of multiple antenna with the power domain NOMA system. But yeah, in comparison from the viewpoint of the industry, the codomain NOMA is actually preferred. So yeah, so I am not in a position to comment much on the MIMO, I mean power domain NOMA and combined with MIMO. Yeah.
All right. So there is another question by Tanvi Sopti. She asks, what will be the security features, requirements, or advancements in 5G as compared to 4G?
Oh yeah, I think yeah, in terms of the security one, 5G has a lot of major enhancement. So basically in the 4G system, the control channel, the control channel is fixed. So this means that as long as someone knows where the control channel locates, we can easily generate some jamming signal to interfere with that control channel, and then in this case, that the entire system may collapse. But for the 5G, we have a more dynamic control channel. So this means that for time one, my control channel may lies in this frequency band, but in time two, my control channel may hop to another frequency band. So this will actually bring us, a lot of the enhanced security for the whole system to be, yeah, away from some jamming interference. So in the end, this will help us to improve the system security. But I mean, if you want to talk about the security issue from some other perspective, so for example, from the cryptography point of view, yeah, that one I'm not able to comment a lot. Yeah, but from the controlling point of control channel point of view, already we are using the frequency hop the control channel to improve the system security.
All right. So
Yep.
there's one more question. It's a kind of more general one. So Yukti Mohan asks, which industries will benefit most from the 5G?
Yeah, I think 5G is just everywhere. Okay, and factory, hospital, city, home, 5G is just everywhere. And it's just like that we have numerous multiple vertical industry. But there's one vertical industry which will shape the future of 5G, which will determine whether 5G will be successful or not. That is V2X communication. Because the V2X communication is one of the major vertical is a major enabler for us to design the autonomous driving system. So whether 5G will be successful or not, it will basically we will see that whether the market will buy it or not.
All right. So I think this was the last question. I do have a question more related to students who are listening to us, so, because we have a student branch attached with us in this collaboration. So my question was, we are all BTech students for now. So do we have any opportunities for research or otherwise in the University of Essex? As we have you from there, so we wish to know more about the University of Essex.
Yeah. In fact, in my university each year, there might be some PhD scholarship, and so you can contact with our faculty member to see that whether if your academic performance is very good, and you may be selected to do a PhD, or you can consider to do a master degree in University of Essex, and other than that, now I'm actually working with a couple of PhD students from IIT Delhi, and actually my friend Dr. Vivek Bahara is an associate professor there, and also and Professor Anai, who recommended me here to deliver this talk. Yeah. So I think we have many ways to collaborate, working together, because of the one is communication, and we can, even you are thousands of miles away, and we have no problem in communicating.
Right.
Yeah.
So I would ask the Rakshit to take over. I'm not sure who is to.
Right. So, like I was saying before, once again, I'd like to thank Sir for being so patient with us, for answering all our queries in detail on behalf of IEEE MSIT. Apart from that, I'd also like to thank Professor Anubha Gupta from IIIT Delhi for making this happen. And at last, I'd like to thank all the attendees and SPS Delhi chapter for making this event such a huge success. And I'd especially like to thank Sachin Motwani from SPS Delhi chapter for his help in conducting this event. Thank you all of you for being here. With this, I'd like to conclude the event.
It was a pleasure. Thank you, sir. And thank you, MSIT, for letting this happen.
Yeah. Thank you. Thank you. Bye bye.
Thank you so much, sir.
Bye.
See you.
Bye. Yeah.